All right, today's lesson, addition and subtraction formula. Sometimes these are called the compound angle formula. And it really tells you, it's really going to show you how to work with sine and cosine at a much higher level than we have in the past. I need to tell you it's a very long lesson. We go through a lot of stuff here. And it starts off very, very complicated, very, very high level. And then it'll sort of come back down to earth. So stay with me through this lesson. It sort of goes out to Pluto, and then it kind of rewinds and comes back a little bit. So if there's moments where you feel overwhelmed or confused, just let it all land, let it all come through before you judge too harshly. The first thing we want to establish is that sine and cosine, and tan as well, all the trig functions, that distribution is not something you'll do with these things. And let me talk about what distribution is for just a second so that word is very clear. When we talk about distribution, like if we have multiplying in front of a set of brackets, what we do is we distribute the 3 onto each part there. We go, oh, multiply the 3 by the x and multiply the 3 by the 2. We can take that operation of multiplication and distribute it over addition. Now, it doesn't always work. I need to tell you, like if you got 3 times xy, you don't do that. You don't do that. That's a wrong move. We just write 3xy. That's the correct move to do that. We don't distribute. We don't do all that stuff. And distribution has sort of come up in other situations. For instance, if we have, say, x squared y cubed, and we have that to the power 4, well, we sort of do distribute the exponent on those. And we get x 8, y 12. But if it was something like this, with addition in there, then we don't distribute. We don't do that, okay? So I need you to understand that distribution was done so much in some situations you believe that distribution is always the thing, and it's just not. And distribution is a specific operation we do when we're multiplying over addition, or when we're doing an exponent law, when it's an exponent to an exponent there. When there's multiplying inside the brackets, there's an exponent outside. It just doesn't work. You don't get right answers if you use distribution in other situations. Okay, now if that's a brain blower, well, I totally get it. It's something that has been taught in pieces all the way through high school and comes together at this lesson. Because what we found out is that, okay, so in this lesson, I need to draw the special triangle for you here that they're using here. They're using the pi over 6 triangle with a pi over 3 over there. And so that's root 3, 1, and 2. And so what they look at is they go, okay, well, if you do sine of pi over 6, you get 1/2. From pi over 6, you go opposite over hypotenuse, and you get 1/2. If you do sine of pi over 3, you get root 3 over 2. So that's opposite over hypotenuse from the triangle there. Take a second and look at it and make sure you're clear on where those are coming from. But if you take these two things and add them together, sine of pi over 6 plus sine of pi over 3, you don't get... we just add them together here. You get 1 plus root 3 over 2. I've just added those two things together. But the thing is, sine of pi over 6 plus pi over 3 equals sine of pi over 2 equals 1. That's what the actual answer is. You can't just distribute these things. When you're adding sine, you can't just go sine of pi over 6 plus sine of pi over 3, because you'd get 1 plus root 3 over 2. But the actual answer isn't that. It's 1. All of that to establish that you cannot do this. This is a no-no with sine. You cannot take sine and just distribute over addition. You don't get right answers. It's awfully tempting to feel ripped off or that's unfair. You go, well, why not? Why can't you do it? Well, because it doesn't work. You don't get right answers. That's why you can't do it. When we did distribution of multiplying over addition, that gave right answers. When you do it with sine, it just doesn't give right answers. That's been established here. Like, for instance, if you go 3 times 10 plus 2, you get 3 times 12, which is 36. You get the same answer if you do it this way. So it works, but for sine, it doesn't work. So now, starting here, right here, in this section, we will derive formulas for sine and cosine of the sum and difference of two angles. And I need to tell you, what they do over the next few pages is not for the light of heart. To be honest, it used to be in grade 13 math, when I was in school, we studied these proofs and we went through them. They're just not deemed as essential, the proofs, in high school anymore. It's sort of been moved to a university type thing. So you could walk through it. You have all the tools. They don't do anything in that proof that is beyond high school math, not at all. But it's not really part of this course, this proof. If you go through it step by step, each piece by piece, and walk through the diagrams and look at it carefully, and you can think of it as sort of an enrichment thing or an AP type thing. What they eventually prove is that if you actually want to do cosine of two angles added together, you can't distribute. You can't just go cos alpha plus cos beta. That's an alpha and a beta, by the way, if you haven't seen those symbols before, with some Greek letters they use in this particular proof. The reason they use alpha and beta is because A's and B's and so on were used for other things, so that's why they went to alpha and beta. And then doing a little bit of stuff that from algebra we already have, they get the formula for cos of alpha minus beta. And a little bit more stuff, they get the formula for sine of alpha plus beta and sine of alpha minus beta. I do encourage you to walk through some of that proof up to the point where it's just too confusing for you, or when you get all the way through it and go, oh, I get all that. This course doesn't ask you to understand that proof, though. This course asks you to use these four formulae. And they may look completely confusing to you at this point, and that's okay. That's my job over the next half an hour or so to try to establish how to use these formulas. The big thing is you don't do this. You don't go distribute sine like I wrote up here. You don't do that with sine. There's a formula of what you do when you have sine, and this is the whole formula there. And it looks very, very complicated, and I'll try and bring that back down to earth. Now, I'm going to do a bunch of examples later on, okay? So I'm going to go through individual examples that are a lot like homework questions, but I just want to establish right now what they mean by using these formulas. So it says find sine 75 without using tables. Okay, that establishes how old this part of the note is that way back when you didn't use calculator to find the answers to sine 75. Calculators couldn't handle that. You had to use tables to find those answers, okay? And then you wouldn't be allowed calculators on tests. You had to look them up on tables. So just a little bit of history of all that here. Okay, so how do you use this? Let's say you wanted to do sine of 75 degrees, which is not on a special triangle. There's no way to get that angle out of the special triangles. So what you do is you break the 75 into two angles that are on the special triangles. So 75 breaks into 45 and 30. And the question that flashes into a lot of people's brains right there is go, well, that's fine if the angles are on the special triangle, but what if they're not in the special triangle? Okay, we'll get to that, okay? One step at a time. For now, we're upgrading our skills to be able to handle angles that are combinations of angles that are in the special triangles. It brings a lot more angles into play here. So what they did here is they took 75 and broke it into 45 and 30. And without getting too carried away right here, they just plugged it into this formula right here and then evaluated each of the individual pieces right off the triangles there. And I'm going to do this a bunch of times coming up. All I want in this part of the lesson is for you to understand what this is used for. These formulas are used that you see here, these four formulas, and there's more of them. These four formula are used to take angles and break them into pieces or to put them back together. That's essentially what those formulas do. And they did that in this question here, is they took 75 and broke it into 45 and 30. And once they had it broke into 45 and 30, then the special triangles could be used to get a really crazy answer here. Now, there's other things that can be done with these, is that you can come up with a formula for tan. Just using the sine and cosine formulas that have already been built, you can build a formula for tan. So there's formula 5 and formula 6. Those are more formulas. We now have a sine formula, cos formula, tan formula. I'm going to review them all in just a second. And even a step really towards the next lesson after this is cosine of 2 alpha, where alpha and beta are the same angle here. So instead of a different alpha and beta, then we say, okay, well, what happens if alpha and beta are the same angle, and we get a new formula? That's really part of the next lesson, so I don't want to belabor that one too much. Okay, what should you understand at this point? You should understand at this point, this is all you really need out of everything I've said so far, is that when you have sine, cos, or tan of two angles added together, you can't do distribution. Okay? The second thing you should understand is, if you want to do sine, cos, and tan of two things added together or subtracted together, you should use one of these formula in this box, addition and subtraction formula. Now, something's just popped up on the screen here called the Trigonometric Identities Toolbox, and this is something we've made at our school here for you to use that has a whole bunch of identity stuff all in one toolbox. If you go to the website, it's a separate file. You can print it out. I encourage you to print it out and keep it near your homework at all times. There's a bunch of things on there that you should already know. and a bunch of things that are new. My screen did a little pop action there. But I really want to talk about this box today, right there. That box right there has all of these addition and subtraction formulas that we've just built. Okay, bring it all back right now. All you need to understand at this point in the lesson is that distribution doesn't work for sine, cos, and tan. So what do? You use these formulas here. Your next question is, how do I use those formulas? Okay, that's what I'm going to do next here, is try and use those formulas to do some stuff. And we're going to jump right in. They get right difficult right off the hop. And I'm going to walk you through them each step of the way. This first question, under my category I called awesome compound angle formula problems. And by awesome, I mean you'll see the power of these compound angle formulas by the time I get to the end here. Okay, so first problem. It says rewrite sine 3x cos 5x minus cos 3x sine 5x as a single trigonometric ratio. This jumps in difficulty to a very high level right off the hop. Now, what I want to look at, I want to spend my time looking at the formulas in this box that I've created back here for addition and subtraction formulas. These formula can be used two different ways. And just as often, you'll use these formulas to go left to right as you will go right to left. This question, even though it doesn't say it, is asking you to use one of these formulas right to left. It starts by saying, okay, take something that's sine times cos, subtract something that's cos times sine. If you look back at those 6 formula that we've built, or that we've had built for us today, we're looking for one that goes sine cos minus cos sine. And I'm going to highlight it here, the one that has sine cos minus cos sine right there. That exact pattern has fallen out in this question, sine cos minus cos sine. And that apparently is equal to sine of x minus y. I'm just going to copy that formula down. The only thing I'm going to do, though, is sometimes these x's and y's, just like you saw in the earlier formulas, the x's and y's maybe are already in the question. See, this question already has x's in it, so that makes these formula a little less useful. So instead of x's and y's, I'm going to write down this exact formula, but I'm going to use a's and b's with it. I'm going to just try and zoom out a little bit so you can see both at once. What I'm going to write is that highlighted formula, but I'm going to write it right to left. I'm going to write the right side first. Sine, oops. My screen's doing a little catch here. 1 second. Having a little screen freeze problem here. Let me just exit that and come back in and see if that reestablishes contact. Nope. Let me go out. Go back in. Oh, there it is. And working again. Okay, so little hitch in my iPad there. Sorry for that delay. Okay, so where was I? I was trying to establish that I'm going to write down that formula right there, but I'm going to write the right-hand side of it first using A's and B's. So I've got this formula, sine A instead of X, cos B instead of Y, minus cos A sine B. Okay, all I've done is write the right-hand side of that formula, but with A's and B's instead of X's and Y's. And apparently, that's going to be equal to, now I'm going to write the left-hand side of that formula, that's going to be equal to sine of A minus B. Okay, so I've rewrote that exact formula that you can see highlighted at the top of the screen. I've rewrote it down at the bottom. I've used A's and B's instead of X's and Y's, and I've wrote it right to left. All of that stuff in one step. Now, once I do that, if you can see in my problem, now I'm going to switch the focus to my problem, is that I've established that exact pattern. You see, the A can be the 3x, and the b can be the 5x. That all lines up nicely now. And what I get is, that means that sine of 3x cos of 5x minus cos 3x sine of 5x, which is exactly what they're asking for, that's going to come out to, okay, well, on the right-hand side of that formula, I got a minus b. My a was 3x. I can see that on the left. My b was 5x. So what I get is, this comes down to 3x minus 5x, which is now sine of negative 2x. Now, I jumped ahead and did that before I really explained what I was trying to achieve, because I want to come back to that. I put it in italics here, even though in the homework it won't always be in italics. And now I'm going to highlight it and really draw your attention to it. What they want is me to rewrite this mess on the left that they've given me there as a single trigonometric ratio. And that's what the compound angle formulas do if you use them right to left. If you go right to left here, you get a single trigonometric ratio. What I mean by that is I started with something that had sine times cos minus cos times sine, and what I ended up with right here was something that only had sine in it. One trigonometric ratio, just sine now. Much simpler, much less going on there. Now, one last step using something from last section is that if you've got a negative inside of sine, you can just bring it up front. So now I've got a really simple formula that came out of a big mess. Okay, listen, folks, I don't think for a second that that is a simple question. There is a lot going on to get that question to land. You have to understand what trigonometric addition and subtraction formulas are all about, that you can use them right to left, and you've got to be able to work with all those variables at once. Okay? Let's read the next question a little more carefully to get ready for what it's trying to say. It says, rewrite cos 75, cos 15, plus sine 75, sine 15 as a single trigonometric ratio. It says, then evaluate. Okay, well, we'll get to the then evaluate in just a second. It says evaluate, rewrite it as a single trigonometric ratio. And when it says to do that, what we're trying to do is use these addition and subtraction formulas to go right to left. See, on the right side, there's all these trig ratios. Sine, cos, sine. But on the left, there's just one. On the left-hand side of addition and subtraction formulas, there's just a single trigonometric ratio. So if we can use these things right to left, we will get a single trigonometric ratio. Let's see if we can. This question here says cos plus sine. I know there's angles in there, and I'll deal with those in a second. But really, we're talking about cos plus sine. So I'm looking for a formula that has cos plus sine. Look them over. That one right there has cos plus sine. So I'm going to write that exact formula down here. And again, this time I'm going to use the x's and y's. That makes it a little bit easier because there's no x's and y's in the question to confuse me now. I'm going to write that formula, but I'm going to write the right-hand side first and then the left side. So it's cos x, cos y. I'm going to try and really line these up underneath the question that was given. And apparently cos x, cos y plus sine x, sine y comes out to cos of x minus y. Now, I don't know if you can see now. If you look right underneath there, I've tried to line them up pretty well, though, that this lines up perfectly for what they're asking me with the x equal to 75 and the y equal to 15. So I'm going to put those in there. I'm going to say, okay, so that means cos 75 degrees, cos 15 degrees, plus sine 75 degrees, sine 15 degrees. That's exactly what they asked for. Now becomes cos of x minus y. Okay, back to the left side again. I made the x 75, and I made the y 15, and now I've done what they asked me to do. I've made it into a single trigonometric ratio. Instead of a whole bunch of cos, sine, all that stuff on the left side, on the right side, I just have cos. Cos of 75 minus 15, I can do a little bit better than that because I know what 75 minus 15 is. It's 60 degrees. Very good. I did what they asked in the first step. Express as a single trigonometric ratio. Done. Then it says, then evaluate. Oh, evaluate. Cos 60. I can do cos 60. Quick drawing of my special triangle here. 60 degrees. There's a root 3 over there. Wow. Let's just clean that up a little bit. There we go. And now I'm ready to do cos of 60 degrees, adjacent over hypotenuse, 1/2. After all that crazy work, the answer here is 1/2. Maybe giving you a hint of why we do these type of things. Sometimes complicated trigonometric expressions become nice, easy numbers that we can use, or nice, easy expressions that we can use, simplifying things down nicely. Okay. Next question. This one says determine the exact value of sine 105. Now, the thing about sine 105, and I've drawn the first special triangle, so I'm going to draw the second one up here, because I'm going to need it in this question, is sine 105 is not on a special triangle, and drawing it on the axis is going to develop into a related acute angle of 75, which isn't very helpful, because it's not on special triangles. But I hope the way I've just drawn those two triangles, you can see exactly what's been chosen here. 105 is made up of 60 and 45, which are on the special triangles. Is there something I can do by, instead of calling this sine of 105, calling it sine of 60 plus 45? Now let's just go to the big picture here. What I can't do is distribution. That's one of the things this lesson's trying to establish, is I can't just distribute the sine. But I do have a formula for sine addition up here. When you add two angles together, I'm going to erase the one I highlighted before, and I'm going to highlight this one now. When you add two angles together, you can break them into individual pieces by using this pattern, sine x cos y plus cos x sine y. And when you're first learning it, I encourage you to, underneath a question like this, write it down, right? Sine of x plus y equals, and then you very carefully go back and you copy each piece down as you're learning it. Memorizing it really helps here. You'd be surprised how fast these things go when you memorize them. So then I get sine x cos y plus cos x sine y, like that. Okay, I'll just copy that straight down there. So I'm using 60 and 45, so instead I'm going to write sine 60 cos 45 plus cos 60 sine 45. And all of these things I can do right off my special triangle. For instance, sine 60, I'm just going to put a little box around this because I'm just using that. It's not really a step in all this. I'm just using that to guide myself. Sine 60 over to my special triangle, root 3 over 2. I said root 3 when I wrote root 2. Look at that. Okay, so root 3 over 2. Cos 45, 1 over root 2 off my other special triangle there. Cos of 60 would be adjacent over hypotenuse. That's 1 over 2. And sine of 45 would be 1 over root 2. And the rest is just in fraction work. This becomes root 3 over 2 root 2. And this becomes 1 over 2 root 2. Yes, I see that radical in the denominator. I'll get to that in just a second. Add them together. I get root 3 plus 1 over 2 root 2. Multiply the whole thing by root 2 over root 2 to get rid of those radicals. I get root 6 plus root 2. Let's see. Root 2 times root 2 is 2 times another 2. I get a 4 there. Maybe you have to go through that for a second to really establish that in your mind. Okay, I did what they asked. I found the exact value of sine 105. And you can just grab your calculator and type in sine 105, and you can get a decimal value. In fact, some of you actually have a calculator that you can get the exact value, exactly what I established here, which is root 6 plus root 2 over 4. But this course isn't about slamming things into our calculator. It's about understanding and explaining where these things come from. So that's a great check of your answer, and you can do that in decimal form or in exact form to check your answer. But you need to show these steps to be able to get marks in this course. Okay, on to the next step in difficulty here. It says, find the exact value of sine 13 pi over 12. Now, there's a host of problems here. One is that it's switched over to radians. I did the previous examples in degrees to try and explain what compound angle formulas do without radians confusing the issue for some of you. And then this angle, 13 pi over 12, it's pretty big, and it doesn't come out nicely. So what I mean by that is I'm going to draw the two special triangles that I just drew a second ago, except I'm going to draw them in radians here because that's what I'm going to need as radians in this question. So here comes special triangles in radians. And then the other one. There we go. Now I've got those two special triangles. Now, first thing we notice is that none of these angles have 12ths in them. What possible way could I handle this if there's no 12ths on the triangles? Well, I'm going to use common denominator to establish that these special triangles have a little more power to them than meets the eye. I'm going to switch these into 12. See, this is 3 pi over 12. And this is 3 pi over 12. And I've just got a common denominator with what the question's asking. It's asking for 13 pi over 12. So maybe switching these angles into the same denominator will bear some fruit. And it really doesn't. Nothing on these triangles adds to 13 pi over 12 because the angle 13 pi over 12 is just too big. So a great first move is to go, well, let's just do a little work similar to what we did last lesson, is to first draw 13 pi over 12 and establish where this thing is. And 13 pi over 12 is right there because this angle here is 12 pi over 12. Oh, that's pi. And I've got 1 extra pi over 12 over there. And you can see what's happened here. So we're already using stuff from last lesson. There's a pi over 12 in there. I want you to be able to see that, so let me just make everything a little bit bigger here. That's a pi over 12 in there. And what that means is that sine of 13 pi over 12 is equal to sine of pi over 12. They have the same related acute angle. The only thing that's happened here is it's switched from positive to negative, so I need a negative out there in front of my sine of pi over 12. Okay, does that help? Now look back at the special triangle. Is there combinations of the angles there that make a sine of pi over 12? And the answer is, yeah, there really is. Many combinations, actually, and you got some choices there. But what I'm going to use is I'm going to break this thing up into a 3 pi over 12 and a 2 pi over 12. And I'm using those angles because they're in the special triangle. So what I get here is negative sine. It's got to be positive, so I need 3 pi over 12 minus 2 pi over 12. Looks completely weird, but all I've done there is taken pi over 12 and broke it into 3 pi over 12 minus 2 pi over 12. Now I'm going to go back, now that I've done that, to what I'm used to, which is pi over 4 and pi over 6. Just to make myself feel better that I go, oh, those are on the special triangle, or those are in the special triangles. I'll be able to handle that. And then now I'm ready to go back to my, in this case, we want sine subtraction. And you look on your sheet there and you go back up and you go, okay, sine subtraction. Where's sine subtraction? Right there. So sine x cos y minus cos x sine y. Sine x cos y, and then it was a minus in between, cos x sine y, like that. Beautiful. Because I can handle all those things in my special triangles. Let me fill them in. Sine of pi over 4 is 1 over root 2. Cos of pi over 6 is, I'm just noticing on my special triangle, and maybe you noticed when I did it, in the midst of talking, I put those in the wrong locations. Nicely fixed up there now, though. Cos of pi over 6 would be root 3 over 2. Cos of pi over 4 is 1 over root 2. And sine of pi over 6 is just 1 over 2. I'll just draw a little line here. I'm going to work up here now. So my first fraction comes out to root 3 over 2 root 2. My second fraction comes out to 1 over 2 root 2. Yes, I see that radical in the denominator. Inside the brackets, I get root 3 minus 1 over 2 root 2. Multiply that top and bottom by root 2 over root 2, and I get root 6 minus root 2 over 4. I'm going to distribute that negative. and I get root 2 minus root 6 over 4. So lots of stuff going on there. Those take crazy practice to get all of those steps built in. And you can see why the first lesson of this chapter was so important. If you don't have that first lesson down pat, you might not have been able to get started on this crazy question. Maybe back down to earth for a couple of examples here. These next couple come a little bit more down to earth. And actually, these really tie well into what happened in the previous section, is that questions like this might have been extremely hard to draw the drawings and establish the answer. And with the compound angle formulas, it all becomes very algebraic, which is nice. They want sine of 2 pi minus pi over 6. So I'm going to first get my sine subtraction formula going here. My sine subtraction formula is sine of x minus y equals sine x cos y minus cos x sine y, just right off the trig toolbox. I encourage you to print that thing out and do your best to memorize as many of these as you can, because it really helps you to do these questions. This question didn't ask for x's and y's. It asked for 2 pi and pi over 6. And it's so nice to write the formula over top, because then you just fill in the angles it's asking for, or that it gave you. So I end up with sine of 2 pi, cos of pi over 6, minus cos of 2 pi, sine of pi over 6. Now here's the thing, and some wisdom has to come from trig here, is that sine and cos are very easy to evaluate at multiples of pi. If I draw sine here, its values at 0, pi, and 2 pi are very easy to evaluate and are nice simple numbers. So they wanted sine of 2 pi here. I can see that comes out to 0. I'm not even going to worry about what cos of pi over 6 is, because it's going to get multiplied by 0. And cos is also very easy to evaluate at multiples of pi, because it's got a value at cos of 2 pi of just 1. And so this simplifies nicely very quickly when there's these pi's involved in there, because the answers just come out to whole numbers of 1, 0, or negative 1. And then negative sine pi over 6, I can go back to my special triangle to evaluate pi over 6. Where was it there? Sine would be opposite over hypotenuse, which is 1/2. So I get negative 1/2 there. Again, really establishing that a very complicated expression often comes out to a very simple answer, and that's why we're doing all these things. That one said find the exact value, and I didn't italicize at that time, because the homework's not going to italicize it. You got to pick these things out and see that it wants an exact value, that it just doesn't want you to type it in your calculator and get the answer. It wants to see the steps. This one says use the appropriate angle formula to create an equivalent expression to cos pi over 2 plus x. And why they say equivalent expression is there's an x in there. I won't be able to evaluate an answer here. It'll have x's in it. And this, in last day's homework, would have been a very difficult question, because it would have been tough to draw the angle. It would have been tough to get the related acute angle. There would have been lots of tough steps here. But doing the exact same question using today's tools, what you get is something that is just very algebraic in nature. All you got to do is write down the compound addition formula for cosine, which is cos of x plus y equals cos x cos y minus sine x sine y, like that. Now, that's not what they wanted. They want cos of pi over 2 plus x. So I'm doing the exact same thing, except wherever I see x, I'm going to write pi over 2. So that's cos of pi over 2. And wherever I see y, I'm going to write an x. If that's a little weird to you, you might have to write down the formulas with a's and b's when the question has x's and y's. But you maybe not. Maybe you can survive this okay. And sine pi over 2 sine x, like that. Now, I also want to establish that finding the values of these things at the pi over 2's is actually pretty easy too, because pi over 2, the values come out to be nice numbers again. for cos and sine. That is cos of pi over 2. If you just look back at my graph over there, cos of pi over 2 is 0. And sine of pi over 2 is 1. And you see, add another couple angles. Pi's and pi over 2's, you just get them right off the graph. It's so nice. Draw a little graph like that very quickly. It doesn't even have to be that good a sketch. You just have to establish where pi and pi over 2 is. 0 times cos x is 0, and here I get negative sine x. A nice algebraic question that last day was done with some crazy, crazy pictures. So really, really doing a sales pitch for these compound angle formulas and getting good at them because they save you a lot of work. Last question of the day, a very, very wild one. I got to draw this out carefully so you can see what's going on here. This question said, if cos x is negative 3/5, where pi is less than or equal to x is less than 3 pi over 2. That's very confusing to start with. What are they talking about? What they're saying is that the angle x is between pi and 3 pi over 2. So it's down here somewhere. There's the angle x. But they gave us more information. They said that the adjacent is negative 3 and the hypotenuse is 5. I can get that right from the cosine. It says adjacent over hypotenuse is 3/5. That's all I can do with that for now. I just want to establish in my brain where this angle is. And then I'm going to do the same thing with y. It says tan of y is 5/12, but y is between 0 and pi over 2. Oh, so y is in the first quadrant here. And the opposite is 5, and the adjacent is 12. All right? So that's my picture of everything's going. Oh, there's y. That's a y. It says calculate of sine of x plus y. So what I'm going to do is I'm going to go sine of x plus y. I'm going to write down the compound angle formula for sine of x plus y. It's sine x cos y plus cos x sine y. Oh no, here goes my, oops. Screen's doing the freeze thing again. There, got unfroze there a little quicker that time. Okay, so they want sine of x plus y. So I want to find sine of x. I look in my picture and I go, okay, I want sine of x. I need opposite over hypotenuse here. I don't have the opposite side. Right off the bat, my picture isn't enough. But with a little Pythagorean theorem, I'm just going to draw a little b on here. And I can go, oh, b squared equals 5 squared minus negative 3 squared. And b squared equals, what, 25 minus 9 is 16. b is the square root of 16. b is 4. Well, it's negative 4, actually. So when I do sine of x, I'm doing opposite over hypotenuse, but it comes out to be negative. You can get the negative from going, oh, I can see it's negative because it's negative y values, or you can get it from the cast rule. See that sine is negative in this quadrant. I like using the cast rule better. Okay, cosine of y is the next thing they want, and that would be adjacent over hypotenuse, but I don't have the hypotenuse here, so just a little work here again with Pythagorean theorem. C squared equals 12 squared plus 5 squared. Let's see, 169. I get c equals 13. So now I can do cos of y, adjacent over hypotenuse. Cos of x, look back in my original picture, I get negative 3 over 5. Sine of y, look over my picture, I get 5 over 13, opposite over hypotenuse. And so I get negative 48 over 65 plus negative 15 over 65. Answer, negative 63 over 65. That is a wild question. Lots of stuff going on there. You got to draw a picture of x and y. You got to do some Pythagorean theorem to get yourself ready for other angles. But the crux of it is that when we're doing sine of x plus y, it's going to ask for all sorts of extra pieces of information. And we're going to have to find out what those extra pieces are. Okay, I hope that prepares you for the homework in a very, very nice way. You've got some nice examples to look back on to see how these compound angle formulas are used, sometimes called the addition and subtraction formula. I've tried to call them both during this lesson. So I can't reiterate enough. You cannot sort of gloss your way through this stuff and just go, oh yeah, I sort of get it. You've got to practice these things and you've got to do all the homework. No time more important than now to really get all these little pieces of the puzzle put together. It's not impossible stuff. It's very new and very weird, and I know that can be intimidating, but you really got to take every day and try to get to the bottom of each particular question.